Okay, so here's our day 2 of this exciting adventure. Are there any questions? Well, I'm excited. That's one of us. Any questions about what we've done so far? Everything crystal clear. Wonderful. When you get a chance, make sure you do the dance around your GitLab project, because that's all getting set up for what we're going to be doing later. The setup for that is, as I mentioned, mostly non-programming stuff around how things are going to be designed. And the thing with discrete event approach, and I'll keep hammering on this as the class goes on, it's very different than what you might have previously encountered in other kinds of simulations, because often they use what's called a time step approach, in which you have a certain discrete time interval, and then you click the clock and then things happen, but only at those discrete times. So discrete time is not the same as discrete event. In discrete event, time is actually, at least conceptually, continuous. Time is actually continuous. Events can happen at any arbitrary time. The only thing discrete about an implementation of a discrete event simulation is the fact of running it on a digital computer means that there's a certain quantum that the digital computer has. So in other words, the only thing preventing use of continuous time is the fact that digital computers can't accurately do that. But since that is extremely small, it might as well be continuous. Turns out that that's a very big deal, because there are a lot of issues with the kinds of results that you get when you why are we doing this again here? There we go. So, right. It turns out that the time step creates some other issues, but for now, in our example, we're going to kind of mostly see what this is about. And one of the canonical examples of doing this kind of simulation is our queuing systems. Historically, these arose in the 1950s, so this is a relatively old approach, and they arose because these queuing models were something that were very important. Some of the early work on that, and it goes back centuries, literally. Some of the most recent work was at the turn of the 20th century by a guy named Erlang. But they were all mathematicians. And so a mathematician wants an equation, an equation that gives you the answer. And what drove them nuts was the fact that in these queuing situations, some very elementary properties could not be deduced through equations. You had to make extremely simplifying assumptions. And there's a whole queuing theory field that has a lot of interesting results, but those interesting results are akin to, there's a drunk guy kind of looking around the ground under a lamppost. And, another guy comes up and starts, helping him. What are you looking for? I'm looking for my keys. Oh, where'd you lose them? Well, in that dark alley back there. Well, why are you looking here? Well, it's bright. Well, that's kind of what it was like. In other words, the simplifying assumptions they had to make made it easy to come up with equations. But as soon as you broke those a little bit, you couldn't come up with that. And so the solution was to simulate it. And so what we're going to do is we're going to first formulate the most basic simulation model of a queue, multiple server queue. And then we're going to actually be the event list. We're going to simulate it by hand to really, and the purpose of that is to really drive home how the event list works. And that's an important thing. Obviously, if we need to run a simulation that's going to run, say, 1 million customers through our system, we're not going to be doing it by hand. But nevertheless, it's important to kind of understand how things are going with that. All right, so what is this multiple server queue? The idea is we have customers, and customers is in quotes because what can be a customer? A customer could literally be a customer, like yesterday we talked about waiting online to get your food at that MWR place by the library. But a customer could be something else. It could be somebody, you could be a web server, and your customer could be somebody coming onto your website. Your customer might be somebody who's requesting a download. Your customer might be something like a call for fire. So anytime that you have a situation where you have a quote server, and server is in quotes because what is in this context, the server is like the person behind the counter. But a server could be like a web server, or the server could be whatever finite resource that has to be totally consumed with kind of doing that. So for example, like at a ticket counter, if you go, whoever's serving you for the ticket, they're dealing with you and nobody else. And so what makes it special, as it were, is that if you come and all the servers are busy, then you wait in a queue. So if you're calling up for customer service, then you will typically wait in a queue because all of our customer representatives are busy. Your call is very, very important to us. Now listen to this elevator music for the next 40 minutes until somebody becomes available. That's a queue. So when a server completes service, that is when the next customer service server is available, then, at some point they take the next person. Now, who is that next person? Now that's where things kind of get a little interesting. In our basic model, it's going to be like first in, first out. But that's not the only thing. So, conceptually, it might look something like this, where you have, so here are our customers. Here are the customers who are already in the queue. Here we have 3 servers. So we're going to have a parameter K, which is going to be the number of servers. These are the customers who have left service here. All the servers are busy here. We have 3 in a process, and then these are the guys who haven't showed up yet. So our system only sees this at this point, the queuing system itself. But in this case, our simulation model will actually see this next guy coming. And then these would be those inter-arrival times that we talked about yesterday. So this is kind of what it looks like. And so here now from that, we can formulate a model. And just to remind, I think, let's see, just for those of you who are online, I'm having trouble seeing the chat. So if you have a question, just unmute yourself and ask it. So remember that a discrete event simulation model has 4 pieces. You have parameters, which are things which do not change throughout the model, throughout a single replication. You have state variables, which do change. And then you have the events, which define how those states change whenever those events occur. And then finally, you have the scheduling relationship, that is which events schedule other events. So here are our parameters. So we have first inter-arrival times, just like we had for the arrival process yesterday. But now, in addition to that, we have a sequence of service times. And these are typically going to be very, very different types of numbers. In most of our models, we will use random variables to do that, but we don't have to. We can just have a predetermined sequence of those values. And then the third is going to be the number of servers. So I hope, especially with this parameter, if we didn't have that, we would have to have a different model for one server, a different for two, a different for three, et cetera. This way, we can have one model, and all we need to do is change the value of this parameter in order to run the same but different model. This allows us to ask the kinds of questions we might be wondering about. So if you're running this facility, one of the questions you might be asking is, should we get another server? Do we have enough? And what are the criteria for that? As we go along, we'll kind of get into a little more depth about that. But with this parameter, I can create one model and then change this parameter and then ask those kinds of what if questions. Or it might be, maybe we have too many. Maybe we need to fire some of them because they're sitting around doing nothing. So I mean, when you're looking at sort of the quote cost of these things, it's like, if I'm literally hiring a server, and typically I have to pay them whether they're working or not. Another context is your servers can be like machines. So many years ago, before in my misspent youth, I was working in a machine fabrication shop, and one of the things that kind of struck me there is that the guy running the place said, if my machines aren't cutting metal, I'm not making any money. So these machines were very expensive. And so if they're sitting around doing nothing, then you're wasting a lot of money. Okay, so those are the kinds of questions we can ask of parameters. Now, state variables. So there are actually a number of different ways of defining the states. In this case, we're going to do it in this way. So first, we're going to define a variable q, which is going to be the number in the queue. And that's now the numbers in parentheses are going to be the initial value. So initially, we're going to, bless you, there's going to be nobody in the queue. So that's a relatively arbitrary choice. That is, we could start with a certain number in the queue, but typically we're going to start sort of empty and idle. S, our other variable, the number of available servers, and that's initially going to be K. So if we have 3 servers, then initially we have 3 available servers. Okay? And then a variable which is often of interest, or just a total number in the system. Now, what's interesting about this is that this is a redundant variable in that it has this relationship with the other variables. So at any point in time, the number in the system is the number in the queue plus the difference between the number of servers that I have and the number that are available. So in other words, so initially, if there are none in the queue, and I have 3 servers total and 3 available servers, then Q plus K minus S is 0. So at any point in time, that's going to be the relationship. So those are the parameters, state variables. Now, what about the events? So we're going to divide this up into, in addition to the run event, there are going to be 3 events. Question?
Not 0. Otherwise, without or is that the specific example?
Well, that's actually a property of the system. That's a good insight. In other words, if there's an available server, then, okay, so you're sitting waiting in the queue and there's a server who's available and ready to serve you. What are you doing sitting in the queue? Wouldn't you go and yeah, exactly. So yeah, no, that's a keen insight. You know, that is true. I mean, that can come up when we're debugging a model. So if we're looking at a model, there are going to be points in time when, well, in the model that we're going to look at, there's actually going to be a point in time where Q and S are both going to be positive, but that's going to occur instantaneously. In other words, that's going to occur only for 0 simulated time. Okay, but very good observation. Okay, so and then one of the things that we want to do is you want to, when you're actually implementing the model, you want to, as much as possible, avoid defining a separate variable for this because of Murphy's Law. Remember that last quarter, one of the things I harangued about is that the optimal number of places where you do something is 1. And so if you are keeping separate track of the number in the system, as well as Q and S, as well as the number in the queue and the number of available servers, then that's redundant. And what that means is that they always have to stay consistent. Now, I mean, it's for a model like this, that's fairly straightforward. But for a bigger model, Murphy's Law says at some point, if these two values are supposed to always be the same, they're going to get out of sync in a large model. And that has been my experience in 95% of the cases. Okay, so we always have a run, and this is one of the nice things, is that when you're defining a model, this is where you start. In fact, you always start with defining your parameters and then your state variables. One of the good things about that is that also once you can do that, then you can always define your run event, because your run event is responsible for initializing your state variables. So here I'm only going to initialize Q and S, and then L is going to be a derived state variable from those. So Q is 0, S is K. That's the state transition for the run event, is the initial value. And like the arrival process, I'm going to schedule my first arrival with a delay of that inter-arrival time. Okay, now I have another event. I'm going to call it arrival, but now in our arrival process, we also had an arrival, and here an arrival kind of makes sense because now an arrival is a customer showing up to our system. But what we're going to do is we're just going to actually put him in the queue first, or her. I don't know what the gender is, but we're going to put that first, an arriving customer is going to go into the queue. And so what does it mean to go into the queue? That means that we have one more in the queue than we had before. That's the state transition. Okay, but they may not stay there long. So if a server is available, then what we're going to do is we're going to schedule another event. I'm going to call it start service, and that's going to have a delay of 0. In other words, if I show up and there's a server available, I'm going to immediately leave the queue and go to them. But as far as this event is concerned, that's not my job. It's somebody else's job to figure out how the server goes. But then, like the arrival process, I'm going to schedule the next arrival with another thing. So embedded in this is actually one of these arrival processes, and we'll kind of exploit that a little bit later. So these are the other two events. Here's that start service event that we scheduled before. And what does a start service event do? Well, when a customer leaves the queue and enters service, now we had a server who was previously available. Now they're not available. And we had a customer who was in the queue. Now they're not in the queue. What does that mean in terms of the state variables? It means there's one less in the queue, and there's one less available server. Rocket science there. Now, once we start service, we want to, well, it's going to take us a certain amount of time. And those times we modeled using our service times. And so we're going to schedule an end service with a delay of that service time. So if it's going to take us, 3 minutes to perform this task, then our end service is going to be 3 minutes after the time now. Now, in these models, all the times are relative to the current time. They're all, and that's what we call them delays. It's going to be a delay from the current time. And finally, the end service. Okay, what does an end service do? That means the customer is left. And so now we have one more available server than we had before. And now one of two things are happening. Okay, so now you're the server. Okay, you've just finished serving someone. What do you do next? Well, there are two possibilities. If there's somebody in the queue, then you should serve them. So if somebody's in the queue, and now notice that I'm translating English statements about our system into mathematical statements about a model. So when I say if there's somebody in the queue, that translates in our model to the value q bigger than 0. This expression means that there's somebody in the queue. If this is false, that is, if q is equal to 0, that means nobody is in the queue. So if nobody's in the queue and you're a server that just finished somebody, there's nobody else waiting, what do? You check your Instagram. I mean, you're basically, you don't have, there's nothing to do. In other words, there's no event that you actually schedule because you're just sort of sitting there until now, in that case, the next arrival, you'll have to serve them. Okay, so and that's the model. This again is and I like to say this because if your concept of a simulation model is a computer program, then I hope that I've disabused you of that idea, because this is a simulation model in every sense of the word. I mean, you cannot define a simulation model that excludes what I've just done. Okay, so then you say, well, okay, that's the pointy-head academics sort of play with semantics and stuff like that. But this is more than semantics. Because this is a real simulation model, implementing this model is something simply translating each of these pieces into code. And so, in other words, I don't have to program, I just have to translate. And that's a very different thing. So even a UML diagram will tell you what the name of the methods are and what the return types are, but it won't tell you what the logic is inside the method. This tells you what all the logic is. This gives you not only the names of the methods, it gives you the logic inside the methods, once you know what that translation is. And that's why the emphasis then is in the hard part. In other words, the easy part is turning this into a running model. The hard part is coming up with this in the first place, as you will discover. Because guess what? I'm going to make you do stuff like that. I'm going to make you both take existing models and turn them into computer programs. That's going to be the easy stuff. The harder one is going to give you a word problem that says, here's a situation, come up with one of these models, define your parameters, state variables, and events. Okay, so, and there's no, I mean, I wish I could say, oh, that's a piece of cake, that's easy, but that requires creativity, it requires thinking. Turning this into a model, you don't have to think. You just have to kind of say, oh, this goes here, this goes here, this goes here. Okay, so now, so now we're going to, just to emphasize this whole thing, we're going to run one by hand, just to really give a sense of what this does. So I'm going to, okay, so I have all this sort of laid out, but I'm going to challenge myself to kind of to not peek and just kind of do it from here. So simple parameters. So we'll have one server. So K is one just for simplicity. So here are our first few inter-arrival times. Here are our first few service times, and then our stopping rules. We're going to run for 2 customers until two finish service, and that's going to kind of be it. So, all right. So what I'm going to do is, yes.
When you're creating the service time Do you know how big that needs to be ahead of time? Obviously, when we use twice, the service time, you can figure out.
Yeah, if that's the case. Now, in practice, these are going to be generated from a random variable generator. So you can have as many as you want.
Dr. Buss, can you repeat the question?
Yes, the question is, if we're running something like this, do we have to have enough values so that we can actually, in this case, actually finish 2 service times? And the answer is absolutely. If I don't have at least 2 service times, for example, and at least 2 arrivals, then we're not going to be able to run it. I need to know what those values are. But in practice, when we implement this on the computer, those will be random variable. They'll be generated. So we have as many of those as we want in practice. Okay. So what I'm going to try to do is, okay, let's see here. Yeah, I'm going to basically just have a little tableau here where we have the current. Okay, let's. For some reason, their default. This to be here, and this to be here. So the current time, current event, and so here we have 3 state variables: Q, S, and L. I'll keep L, and then the scheduled time and the scheduled event. So I'm just going to keep a tableau here of what's going on. These last 2 columns are the event list. And here, let me. Okay, I'm going to need my values. Let's take those and just paste them in here for reference. Okay, so here are my values. Now, here's the way it always starts, basically undefined. Everything is undefined, but remember that the very first event on the event list is going to be our run thing, and that looks awfully small. So I'm going to try to increase our, where are you here? Come on. Let's make this bigger. Oops, too big. Okay. Everybody see that okay? Okay, so when the event list starts up, this is how things look. So in other words, these are all undefined, and the run event is on the event list at time 0. And what I'm going to do is I'm going to put just to kind of emphasize this is one iteration. I'm going to put a line under each iteration. So this is important to understand. Okay, so the way the event list works is at any point, at every iteration, it takes the next scheduled event, and that becomes the current time. It takes the next scheduled event, that becomes the current event, and then it executes that event. So basically, we're going to, right now, this is the event list. And so the earliest event time is 0. And so we basically, so in this tableau, I'll just move that down here. Okay, so I've just taken the earliest event and moved it to the current time, the current event. So then now they're defined. And temporarily, our event list is now empty. So if we don't do anything else, it's just going to end. Now, what is the run event? What is the run event? The run event says we initialize Q and S, Q to 0 and S to its value. So Q is 0 and S is 1. Now, remember L, remember L is Q plus K minus S. Let's make that bigger. Okay, so if Q is 0 plus 1 minus 1 is 0. So, and there's nobody in the system. Okay, so now what else does the run event do? It schedules the first arrival with the delay of the arrival time. So what's the first arrival time? Can I move this down? Oops, down. What are you doing? Can't I move you? Oh. Okay, the first arrival time is 2.1. So at time 0 plus 2.1, we have an arrival. And we've now used up this value. That red just to emphasize it. Okay, so we've used that value up. And that is the end of the iteration, by the way. So we just schedule the arrival, that's it. So that's an iteration. Now the next turn of the crank is we advance. So currently the event list, this is the event list right here. This is the whole thing, just one event on it. But nevertheless, the logic is we advance time to the next scheduled event and pull it off the event list. So what's that next time? It's 2.1. What's that event? It's the arrival event. What does an arrival event do? All it does is it adds one to the queue. It doesn't do anything to S. But now L is now we have 1 plus 1 minus 1, and that equals 1 last I checked. Okay. Now what does an arrival do? It schedules the next arrival. So let's, the next arrival happens at time 1.4. 1.4 plus 2.1 is 3.5. Okay, so we've used up this one. But then it also schedules. Okay, so now if S is bigger than 0, it will schedule a start service. Is S bigger than 0? Last I checked, 1 is bigger than 0. And so it will schedule a start service with a delay of 0. So it's still time 2.1. And it will schedule that event. And now this is the end of the iteration. And so we now have 2 events on the event list. But then we kind of, that's the end of the iteration. So that's the important thing about events. It's the principle of that's not my job. So it's not the job of the arrival to worry about what the server. So if you're thinking that, okay, this first guy showed up, there's a server available, let's go right into, stop thinking. Just work with the event itself. Okay, so now this is the event list. We have 2, but what's the rule? So I got to be careful here if we're doing it by hand. If I pick 3.5, this next arrival, what's that? Okay, that's interesting. Evidently, the people online can, their mouse shows up here. So, okay, cool. Interesting. The things you learn out there. All right, so you pick the smallest one. What's the next scheduled event? It's that 2.1 start service. So 2.1, just that event. Nothing else. And what does start service do? It takes 1 away from the Q. So Q is now 0. It takes 1 away from S. S now 0. And now, let's see, 0 plus 1 minus 0 is still 1. So that is working there. Now, this arrival is still on the event list. So we never take, the only way to come off the event list, at least for now, is when it bubbles up to the top. So don't lose events. That's important. Okay, but then what about the end service? So we schedule an end service with a delay of 2.2. That's the thing. So 2.1 plus 2.2, last I checked, is 4.3. Okay, and then that is all for this event. Okay, so see, what these lines are, each of these lines is an iteration. So it's not one continuous thing. It's just each of these consists of one turn of the crank, and you just keep following the same logic each time. So what's the earliest of these two events? Well, in this case, it'd be that arrival is 3.5. Okay, we take that arrival off the event list. What does an arrival do? All it does is it adds 1 to the queue. It doesn't change S, but now we got to worry about, let's see, how do you move this thing? Okay, Q. All right, so Q, now there are actually 2 in the system. Now, what is the logic in arrival? The logic is that if a server is available, we schedule a start service. But is a server available? No, because S is equal to 0. So we don't do anything. So, well, we don't do anything as far as that is concerned. Now, we still have this 4.3 end service on the event list. But the arrival also, so we let's see, we used this up already. And now we need to schedule the next arrival, which is a delay of 3.5. 3.5 plus 3.5 is 7. So now the next arrival is going to happen at time 7. And now we need to add some of these guys. And this is the, oops. Okay, so now I hope you've sort of seen that this is just a very mindless turning of the crank where you find the next earliest event. In this case, it's the end service. Okay, what does end service do? It doesn't affect Q, it simply adds 1 to S. And now you can double check my math, L should be 1. And what does an end service event do? Well, it says if there's somebody in the queue, meaning if Q is bigger than 0, we're going to schedule a start service immediately. So what time is it now? It is time 4.3. We're going to schedule a start service at that time. And again, you can never lose an event. This event is still there. And we're going to need a couple more. And again, this is the last turn of the crank there. And then finally, or not finally, but okay, we have 4.3. We have a start service. What does it do? It decreases Q by 1, it decreases S by 1, and L is still 1. And then we need to schedule the end service, which is going to be at time 1.3. 1.3 plus 4.3 is 5.6. And we still have this arrival. And that is this turn of the crank. And now, okay, the 5.6 end service. I hope you're getting the idea of this. It doesn't affect Q, increases S by 1. Now there's nobody in the system. And we're now that there's nobody in the queue, it doesn't do anything. And now this is the, oops. Okay, so this is our second end service event, and so by our rules, we're done. And so this is actually, again, just as the model that was described in those slides is in every sense of the word a simulation model. we have actually run a simulation in every sense of the word. And notice a couple things. We have not written a line of code. Now we've done it by hand. So we are the simulator. We are the simulation engine here. And again, that's, I torture you with this mostly so that you have a really crystal clear understanding of how the event list works. And this is important because the mindset is very different than one for a time step, and it's also one where if you think too much, you can kind of get wrapped around the axle. If you kind of stop thinking and only work the algorithm, and what is the algorithm? It is we start with the run event on the event list. And so that's kind of the bootstrapping that kind of gets things going. And then from then on, the rule is exactly the same. You advance time to the earliest scheduled event, next event, remove it, and process it. What does process it means? Executing the state transition, that's what we're doing, and then scheduling any events, if any. And as we've seen, sometimes you don't schedule any events. That's okay. One mindset to avoid, especially in a model like this, is that, and for some reason this comes with certain other baggage or orientations, is that when you have like this guy that arrived here, was not able to get service right away because the server was busy. So it may be that a mindset that I've encountered in the past is that, okay, that guy is kind of waiting around for something to happen. And physically, yeah, if you're the guy, you're waiting around. But as far as the model is concerned, that's not happening. As far as the model is concerned, the model doesn't know anything about any of this. All the model knows about are these variables. It knows about Q, it knows about S, and if you've included an implicit event like L, it knows about that. It just knows those values. It doesn't know anybody. They're not waiting around for anything. Basically, every time an event occurs, you get that one shot to maybe schedule events. And if the condition for doing it isn't there, then too bad, so sad. So the thinking, and this is where, I mean, it's understandable because again, that guy is waiting for something to happen, but that something is not going to happen from that guy. It's not going to happen from that arrival event. That arrival event is not sitting around waiting for something to happen. The event happened and it's gone. It did its state transition. It scheduled its events. If it didn't schedule any events, too bad. Because that guy got executed. I mean, he got service when the server became available and scheduled the start server. In other words, it was another event that allowed that customer to kind of go to the queue. And hopefully, let's see if I scroll to. Where are you here? Let's see how I did. Okay, so it looks like I actually got the numbers right this time. That's in the past I've kind of screwed up on the math, but anyway, so you can kind of see exactly how that works. And here, particularly with this diagram, it makes it absolutely clear, a little bit more clear, that these are kind of separate iterations, and that's an important concept to kind of really have there. Okay, so what have we produced? What we have actually produced, though, is this state trajectory. We produced a state trajectory for each of our 3 state variables. And So if we look Q, it was kind of zero. It kind of popped up instantaneously, but then it went to it went up to 1 and stayed there for a little bit of time, and then it went back down. And likewise, the variable S, the number of available servers, it was it was 1 for a little while, but then for the rest of the time, it was pretty much busy the whole time. And our variable L, well, it's kind of started at 0, but then when that first guy showed up, it popped up to 1, then it popped up to 2, and then back down to 1, and then all the way back down to 0. So those state trajectories are what we're after. Everything we want to find out about this model is included in the state trajectories, and nothing else. Because the only things that are changing are the state variables, and the only information we have about those states for a particular replication are in those state trajectories. Now, here's the thing to understand for next time, is that now we're going to, for this little model, we're actually going to get some measures of, in other contexts, you're going to hear differences between measures of performance and measures of effectiveness. In this context, they're just measures. It doesn't really matter. But what might we want to know about a system like this?
Maximum L.
Yeah, exactly. So why might we want to know that? Exactly. Yeah. So if we're designing a system and we say, well, how big, if there's a finite amount of waiting room, how big should we make it? And it's easy to kind of screw that up. Have you ever been driving down Del Monte and In-N-Out Burger has the cars all the way out to the end? Okay, that's a situation of a finite waiting room, and where they kind of screwed up, I think, because it's every time I go there, they're backed all the way up. Now, what's interesting is in the model we've done here, that doesn't exist. In fact, it's kind of the way they behave. They back all the way out onto Del Monte and clog it up. But in other words, there is no finite waiting room in this particular model. But that is something, say, well, that's something that we might want to investigate. Is, in other words, if we are designing a system in which, okay, how big to make the waiting room or the amount of waiting place, we need a model which is going to kind of do that. This model doesn't, but the modeling process, and that's is this reason this is relevant. The modeling process, at least the one that I advocate, is to always start with the simplest possible model, and then examine the assumptions to see whether or not they hold up against what you're dealing with. So we'll talk about that in another class. But for right now, what else might you want to know?
Look for a trend, US or L. See.
Oh, yeah. Will it reach steady state or not? Yeah, and that's something which, in this particular system, we have no idea about. But that's a very relevant question. But some other things we might be interested in is what is the average number in the queue, for example? So yeah, it'll go up and down. Maximum is important. But what about the average? Knowing that there is going to be a queue, is there like an average? Another might be, well, what about our servers? What is their utilization like? Utilization is like, what percentage of the time are they busy? What percentage, so like my former boss who said his machines are only making money when they're cutting metal. So cutting metal is being busy. Sitting there not cutting metal, they're just kind of being wasteful. So can I get a measure of that? And can I get a measure of that? One way to be kind of go to the shop and figure all that out. But another might be, should I buy another machine, or should I get rid of it? Should I sell a machine? Well, you can ask a question like that of this model without ever having to actually go through the physical thing. So those are things we're interested in, and especially these averages. I think you're taking a stats class now, or? Yeah, okay, yeah, so averages are important, they're not the only thing. But now here's the interesting thing about the averages that we're going to be dealing with, at least initially. How do you take an average? Yeah, you add them up, divide by the number. Is that, if I wanted to know the average number in the queue over the run, is that the way I can do that? Exactly. In other words, if I have a discrete set of observations, then adding them up and dividing by the number, that's the standard way to go. Why? Because the data that statisticians have always had are what's called a random sample, just a discrete set of data. But this isn't discrete, and you're spot on, because the amount of time I spend in each state is going to be important. In other words, if I spend more time in a particular state, that value shouldn't be counted as much as all the others that spend shorter amount of time. So how do I go about doing that if I can't just add them up and divide? And that's what we're going to talk about tomorrow. And so, so just kind of read ahead in the discrete event modeling. Let's stop the share. Are there any questions from the online folk? Okay, well,
not particularly, but I do have an observation just kind of for class logistics. If you could repeat what the folks live are saying, that would be
okay, yeah, thanks.
helpful.
I'm still getting used to this hybrid thing. So you weren't able to pick up what they were saying?
Most of the time, no.
Okay, yeah. Well, it might show up on the recording. If not, if there's something that was asked that you didn't know about, well, is there anything I can answer right now?
Without knowing what was initially asked, no.
Okay, well, it's yeah, I mean, basically we're just talking about how to find an average when the amount of time that you're spending in each of these possible states is going to be different. And that's what we're going to talk about tomorrow. Okay?
Sounds good.